So welcome. So I thought what we'd do today is we'd go over the problem solving session questions for Module H. And what I'm doing today is I've done the problems. Rather than me writing it in front of you, I've already written it out. Saves a bit of time, I think, and I can lay things out a bit better. There's 4 questions. Let's go through them and we'll see how they go. So try not to look at the answer until we've read the question. So write the equation that links the capacitance of a capacitor, the distance between the parallel plates, the cross-sectional area of the gap between the plates, and the dielectric constant of the material in the gap between the plates. And in there, I'm trying to build a picture of you, build a picture and ask you a question. In this case, I put down the common symbols for capacitor, area, distance between the plates. I needn't do that. I could just use words. But in my mind, what I do is I say, if you follow my little arrow, in my mind what I say is that capacitance is big C and separation is little d and gap area is big A and dielectric constant is this funny K. And I do a funny K because there's so many times we use K, it's easy to get them all confused. Now in my mind I have a picture, and I have a picture of a parallel plate capacitor. In this case I'm using a circular plate, and I'm trying to specify in my mind what these letters really mean. And basically the D is from one plate to another. That's pretty obvious. The A is sometimes confusing. People think it's the area of one plate, and then they say, well, we've got another plate, so is it both areas or is it one of them? And it's actually the cross-sectional area of the gap. So if the two plates are truly overlapping, it happens to be equal to the area of one plate. But if I move the plates aside from each other, so there's only a little bit of overlap, there's only a little bit of this area. So it's good to have a good visualization of what the area really means. And then the dielectric constant is this. It's a figure of merit, it's got no units, and it's how much the polarization of the medium that's inside between those two plates multiplies the effect. And in class I talk about how the polarization does that. So I'm looking at those symbols and I'm going jog, jog, jog. Oh yeah, I remember. Capacitance is equal to the dielectric constant, area of the plates, of the cross-section of the gap. Epsilon naught is this constant not even mentioned in the question. You've got to know it's there, divided by D. And you've got to know that equation. And then sometimes I say, well, what happens if you don't know that equation? And so I'm put a little note down here to you, and I said, sometimes you can work out a formula that you cannot remember by looking at the units. A good example would be, well, if I remember that acceleration is meters per second squared, which is meters per second, and I had something with velocity of meters per second, I had something with time, which is seconds. I kind of know not to multiply those two together, but divide the velocity divided by the time. It's that kind of thing. It sometimes helps, but it doesn't always work. This does not work so well with compound units like the farad. What is a farad? It's a farad. Well, it's not. That's a name. That's named after, I think, a person. Like Newton was named after a person. And so you can't look at farad and go, oh, I know what to do now mathematically. Also, it's not under note, but also it doesn't tell you if there's any constants in there. If it's like a half mv squared, it would miss the half. So the trick is you learn your equations early and you keep studying them. You don't just learn them once and forget about them. Keep that equation sheet by you and study them. Anyway, there's the answer. You could, I suppose, you could turn around and say, well, as the area gets bigger, I expect the capacitance to get bigger, so A goes on top. And as the D gets wider, I expect the capacitance to get less. Otherwise, a plate on Neptune and a plate on Earth would have a huge capacitance and we'd notice it. It's got to get smaller with distance rather than bigger. So D must go on the bottom. But I fear you wouldn't know what to do with the dielectric constant, and you don't even know about epsilon naught. So you got to learn them. Cool? Let's go to the next one. Get in between the little green lines. An air-filled capacitor shown has a, at the side, has a capacitance of 8 farads when the gap is filled with an insulator. The new capacitance is a value of 18 farads. What's the magnitude of the dielectric constant of the insulator? Now, people can intuit this and they can say, well, if the capacitance doubled and nothing else changed other than the dielectric, then the dielectric constant must have doubled. If it tripled, then the dielectric constant must have tripled, because that's the only thing you're changing. And you can do it like that. But let's say that you're not so comfortable doing the intuition like that. How would you more formally do it? And so, first thing is to visualize. And you say, well, here's my old capacitor, and it was air-filled. So I know that an air-filled capacitor, air, like a vacuum, has a dielectric constant of 1. There's no benefit from having air inside the gap over having a vacuum inside the gap. So the capacitance is not improved or increased. So the dielectric constant for air is the same as the dielectric constant for vacuum, which is 1. Okay. And for the new one, I've put a different color of filling in to indicate that the material had changed. And it's now, the capacitance has now gone to 18 farads, and the dielectric constant, I don't know what it is. And then just to finish this thing off, I know I'm going to use C is equal to K A epsilon naught over D. So what about A epsilon naught and D? Well, A of the new is not changed, so it's the same as the A of the old. And the separation new is the same as the separation of the old, because it's not changed. It says the gap, not a new gap, but the gap when the gap is filled. And epsilon naught is a universal constant, but if you like, we can call it epsilon naught new and epsilon naught old, you know. Then for me, what I tend to do is if it's not changing, I call the old one 1 and the new one 1. I try to always start off with the old thing being 1. It makes the math so much easier. So rather than going A naught, A0, A old and A new, I'll just put down 1 and 1. It just simplifies the equation. Then I say, well, let's do ratios. We always do, when we're doing a ratio, we always do this layout where we say the new capacitance over the old capacitance is equal to, well, it's going to be 18 over 8. And then I didn't leave myself enough space when I did this, so I messed up. I forgot to put the D in. So then I go to this equation and I go, well, it's the new dielectric constant and my new area and my new epsilon naught, I know it doesn't change, over my new separation divided by my old dielectric constant and my old area and my old epsilon naught divided by my old separation. And so I say, well, C new over C old, the new capacitance over the old capacitance is, well, it's 18 over 8. And that's going to be K new over 1. Because I know the old one was 1, I don't know what the new one is. And then I'm doing area is 1 over 1, because it doesn't change. And epsilon naught, 1 over 1, because it doesn't change. And my separation 1 over 1 because it doesn't change. So it seems to me that just equals the new dielectric constant. So 18 over 8 is the new dielectric constant, and if you work that out, that comes up to be 2.25. No units, it's just a figure of merit. Now, I suspect what you're saying is, I could have just done that in my head, and 9 times out of 10 you can. Every now and then you'll get it upside down. And that's the problem. Every now and then, especially when, I don't know, maybe when you're rushed, maybe when you're under stress, maybe when you're in a test, you'll get it upside down. And that's wrong. You get no points for it. So it's worthwhile slowing down and just doing it right. Cool. Let's go to the next one. So this next one, my lines are not lining up like they should do. I'm going to have to move this around a little bit. So, third question, what is the equivalent capacitance of this network? We have a network, a circuit with 3 capacitances in this case, and I want to reduce it to 1 capacitance, whatever that happens to be. And I look at this side and I say, well, it's a series section in a parallel circuit. And I make a note, down here at the side. There are 2 classic networks. There's a series section in a parallel, and that's what we've got. Do the series first. And then there's a parallel section in a series network, and you do the parallel first. You do the unambiguous bit first. So this top capacitor is in parallel with the left-hand capacitor, but the problem is so is the lower capacitor is in parallel with the left-hand one. So they both are in parallel. So the only thing you can say for sure is that, unambiguously, is that that top capacitor on the right is in series with the bottom capacitor on the right. So do that first. And for the one over here, which is the parallel section in a series network, you know, the bottom left is in series with the top right, yeah, I suppose. And the bottom right is in series with the top. The only unambiguous thing is that these 2 guys are in parallel with each other, so do that first. So you look at which one you've got. Then the other thing you've got to do is know your equations. For parallel capacitors, you just add them together. So C parallel is equal to C1 plus C2 plus C3 plus, you know. And for series capacitors, it's 1 over C series equals 1 over C1 plus 1 over C2 plus 1 over C3. And it continues. There's a bit of an issue here, because if these were resistors, the mathematical form for series resistors, this just adding them together, it is just adding them together, which is the same as the mathematical form for the parallel capacitors. And the mathematical form for the parallel resistors is like the mathematical form for the series capacitors. So it's like there's this mathematical form and they swap. So my advice is you learn one of them really well. You learn what goes on with resistors really well, and then you remember its opposite for capacitors, or you learn capacitors really well and you learned its opposite for resistors. Yeah. I learned the resistors first, so that's what I remember. So we have our original network and we've got to figure it out. So we're going to do the series bit first. So 1 over C series equals 1 over C1 plus 1 over C2, which is 1 over 4 plus 1 over 8, which equals 2 over 8 plus 1 over 8, which equals 3 over 8. And I can't tell you how many students will tell me that that's the answer. But in fact, C series is 8 over 3. You've got to flip it. And fair warning, if you're not writing down this initial equation, if you're just, that's in your mind and you're just writing down numbers, there's nothing on that page, 1 over 4 plus 1 over 8, to tell you that you're supposed to flip them. I learned the hard way. You want to write down complete sentences. Write down something equals something and make sure it's a correct statement every time. Don't use the piece of paper as a jotting pad. It doesn't work. The more you write down, the less you keep in the head, the better you'll do. Again, especially in a test. So, okay, so we reduced these two. We managed to get one single capacitor at 8 over 3 farads would replace that 4 and that 8. So the next thing we say is, well, let's add those two together. So now we have a 14 on the left, like we had before. And now we have a single 8 over 3 at the right-hand side. And now they're in parallel. So I go C parallel equals C1 plus C2, which equals 14 plus 8 over 3. Okay. C parallel is equal to, well, 14 times 3 is 42 plus 8 over 3. 42 plus 8 makes 50. 50 over 3. And then we have that. So 3 goes into that once. Carry 2. 6 3s are 18. Yeah, etc. Do your math. So on a test, typically you'll either get the series section in a parallel network or the parallel section in a series network. So make sure you can handle both of those. And this last one is oh, you are joking. I'm going to pause. So I'm back. So I couldn't get the bottom of the page. It's just... Okay, last question. So write the equation that links the energy stored inside a capacitor, on a capacitor, which is U, to the charge on the capacitor, which is Q, and the potential difference across the capacitor, which is delta V. Again, I do believe in visualizing, so here's a picture of the capacitor, kind of not looking from above or looking from below, but kind of looking inside it. And if you look, you'd see all these positive charges on the top plate, and you'd see these negative charges on the bottom plate. And I'm kind of showing them connected individually by the electric field, which is not the case. They're actually spread out all over the place. But, you know, I'm just trying to get you across this idea that the electric field goes from the top plate to the bottom plate, and we can describe it by a series of arrows. The external circuitry, I have this battery connected, and the battery voltage is delta V, and we have the Q positive on the top plate and Q negative on the bottom plate. And I'm trying to define my terms here, so I say, well, U is energy and Q is charge. Do I mean charge positive or charge negative or both, not worrying about the signs, or do I mean the sum of the charges? I get different answers for all of those, so I need to be a bit clear about that. And delta V is the potential difference. All right, let's say I can't remember the equation. Learn the equations. you should just write this down. But if you don't remember the equations, what do? And you say, well, maybe I can use the units. You know, well, it's a compound unit. It's joules named after a person. And it's coulombs, which is named after a person. And it's volts, which is named after a person. So none of these are simple units, not basic units. But I do know, I remember, that volt is equal to a joule per coulomb. It's how much energy each coulomb of charge holds that you gave it. So hold on, if volts equals joules per coulomb, and I have joules and I have coulombs, then joules per coulomb times coulombs gives me joules, which is energy. So I go, yes, U is equal to Q delta V. But it's wrong. And the reason why it's wrong is because, as I said, using units doesn't tell you about coefficients. This would work if I had a certain energy and a certain potential difference, and I just was able to add more and more charge at that voltage. So if I had charge flowing from one battery to another, and it's just how much going through a resistor, how much energy is dissipated in that resistor. Well, I know the coulombs of charge coming through. I know the potential difference they drop inside the capacitor. Joules per coulomb works. Joules times your joules equals your volts times your charge. Potential difference across, charge through, it works. But this is not that case. this is a case where you get more charge on the plates and that creates more potential difference. It's not the voltage of the battery that, well, it's not the voltage of the battery that we're talking about. It's the voltage across the potential difference across the plates. Shame on me. I put down delta V there for the battery because eventually the plates get to delta V. Shame on me on that. So the voltage across here starts at 0 because the charge on here starts at 0. So I start off at the origin of my formula, of my graph. And then as I put more charge on the plates, I get more voltage. If I double the charge, I double the voltage. So I get a line which is a straight line, 45 degrees. The energy is equal to, if you like, the integral of Q delta V, which is the area under the graph. And so it's a triangle. So it's going to be half Q delta V. And I just don't think that, you know, again, learn the equations. But that's where that thinking comes from. Okay? I hope this helped. I hope you like the layout of writing the answers first. I think it gives you a better appreciation of what's going on. Okay? I may put this PDF on the site as well as the video. That way you get all three. Okay. See you soon. Bye-bye.